Good afternoon.
Good afternoon.
All right, last class we stopped in the middle of our second example problem. So this is 12.102. So let's take a look at it again. So the problem says, consider a thin, opaque, horizontal plate with an electrical heater on its backside. The front side is exposed to ambient air that is at 20 degrees Celsius and provides a convection heat transfer coefficient of 20 watts per meter squared Kelvin. Solar irradiation of 800 watts per meter squared and an effective sky temperature of -40 degrees Celsius. And then they gave us those figures you see I redrew on the right. And then it says, what is the electrical power, watts per meter squared, required to maintain the plate surface temperature at Ts equal to 60 degrees Celsius if the plate is diffuse and has the designated spectral hemispherical reflectivity? All right, so we were given thin, opaque, horizontal plate. It has an electric heater on its back. There's a T infinity and average convection coefficient 20. So we have what the area is right above the plate. And then we have solar irradiation coming in, right? 800 watts per meter squared. And then we have the temperature of the sky. So that's far off of the plate, far away from it in the sky. We have the temperature of the surface of the plate, which is 60 degrees Celsius. And it tells us the plate is diffuse, okay? So we are looking for the electrical power. They gave us this schematic of what's going on, and then they gave us this reflectivity as a function of wavelength, right? So it goes 0.2, and then at 2 microns, it goes to 0.7, okay? All right, so we had assumptions. We said plate is diffuse, which was given. It's opaque, which was given, so we put that. We have steady state, and then we said the sky emits as a black body, okay? All right, so we did a COE of a plane wall. We went through, canceled off because it's steady state, drew that we had irradiation coming in from solar and then from the sky, and there's an absorptivity on each of those to tell us and show us the amount of energy that actually goes into our control volume there, okay? And then the plate has emission, so emissive power coming off of it, E, and we have convection, right? So then doing that, we put those terms in there, put our emissive power, and have our Newton's law of cooling. So we started putting in there, we said for the sky, behaves as a black body. So then the irradiation coming in from the sky is the same as what's the black body of the sky is emitting then, which is Stephenson-Boltzmann's constant, temperature of the sky to the fourth, right? All right, so that simplified us, and then we saw what we had as our unknowns, and we said we're diffuse, but we can also make the assumption of gray, and gray surface allows us to say that for between the sky, the absorptivity of the irradiation coming in from the sky and the emission off of the plate, the emissivity, there we can say gray that they're independent of wavelengths because the temperatures are so close. So independent of wavelength, okay? And that's because the temperatures are so close. We can't say it for the absorptivity of the solar irradiation and the emissivity of the surface because the temperatures aren't that close. So the wavelengths has more of a dependency then. All right, so then we started off with our solar absorptivity of our unknowns to solve for, right? And we set it up as this, okay? So we have just the general equation for absorptivity And I think this is going to go away from S, subscript S. That should be for solar. Okay. And so we have on the top, we're integrating over all the wavelengths of what that absorptivity is times the irradiation. Okay. And then on the denominator is just the integration over all those wavelengths of the irradiation. So that would be the total irradiation because you're integrating over all the wavelengths. That's just the total. So what we did then is transformed the irradiation and we said this is solar irradiation. Okay, so spelling irradiation. So in this case, it's solar irradiation. So we change basically what's coming from the sun. So our irradiation onto our surface here, okay, is the same as what's coming off of the sun as emissive power. Okay, so we've changed it from right here, from irradiation to emissive power of the sun. Okay, because the sun behaves as a black body, so we have an understanding what a black body emissive power is as a function of wavelength. Okay, so then we have to we have to integrate over all the wavelengths. So wavelength times that emissive power, we're integrating over that over the whole spectrum. Okay, and then on the denominator, it's just the emissive power over all the wavelengths, which is the same is just the black body emissive power, which would just be Stephan's Boltzmann's constant, temperature of the fourth of the sun. Okay, that's the same thing as the total. I should say this is not just that part, that's all of it. Integrating over the whole thing. Okay. All right, so we said, okay, we don't know the absorptivity, right? We were given reflectivity, okay, as a function of wavelength. So how do we get that? So we looked at the equation basically of we're relating all the irradiation coming in at a given wavelength would be either reflected at that wavelength, absorbed at that wavelength, or transmitted, right? And we can cancel G out of all these terms, and you get 1 equals reflected, absorbed, transmitted. Our surface is opaque, so there's nothing being transmitted, okay? So then that means we can relate the absorptivity to 1 minus the reflectivity at any given wavelength, okay? So we can take our reflectivity and just 1 minus it, because 20% is getting reflected. That means 0.8 or 80% is getting absorbed. And then it goes to 0.7, 70% getting reflected, 30% absorbed. Okay, so that's our plot for absorptivity. If anything is confusing, you just let me know and I'll stop or need to re-explain. All right, so that means if we integrate over all the wavelengths, all we have to do though, since the absorptivity is changing from 0.8 to 0.3, we can break it up, that integration, and just go from 0 to 2 right here, and then from 2 to infinity right here, okay? And break up this integration. So that's what, since the absorptivity is constant over that sections, okay? So we pull the absorptivity out and just have from 0 to 2 on the numerator. And again, this bottom is the total emissive power. So that's just the whole overall the wavelengths. And then from 2 to infinity is our next step of our integration on the right. And we have then what I have circled is now this factor F that we have in our table, but we can look at it as that factor F replaces everything that I have circled there, and this, everything that I've circled there. So we have then this F 0 to 2 is the fraction of solar emissive power emitted from 0 to 2, and this factor with 1 minus that factor 0 to 2, that's just the remainder, the fraction of emissive power from 2 to infinity. Okay. All right, so we also know that from our plot, the first step of absorptivity is 0.8. The second is 0.3. All right, so then we still need to get this factor. How do we do that? Where do we get this factor?
To the table.
Yeah, so when we go, we have a table of 12.2 has basically given us, as a function of wavelength times temperature, they give us this factor of 0 to some wavelength. Okay. So we have then a whole bunch of values. Okay, so if we want our factor, we need to get our wavelength times temperature. All right, so if we need this wavelength times temperature, what wavelength do we choose? All right, so this figure, or this table of what this is really putting in a table form, this table kind of, if we plotted these two columns, and on the denominator, in the x-axis, we have wavelength times temperature. On the y-axis, we have this factor of 0 to some wavelength that you're looking for. This is going to look something like that, okay? So it goes from 0%, right, nothing of the emissive power fraction, to 100% when you go all the way to infinity, okay? So if we're looking for 0 to 2 microns of the fraction of emissive power from 0 to 2, what do we think we're going to need to look up, use as our wavelength?
Two, or well, yeah.
Yep, 2, right? So we'd have 2 microns, right? What's our temperature that we're going to use?
Solar temperature?
Oh, sorry, I didn't catch all that.
Solar?
Yeah, the solar. So the sun is 5,800 Kelvin. So it's whatever the source of that radiation is from is irradiation. So this one's the sun. So that's 5,800 Kelvin. Okay, so we get 1160 microns Kelvin. Okay. So then we can use our table, and we get our factor. And that is 0.941. Okay, so that's the table. All right, so we actually have everything to solve, but I'm going to redraw it or rewrite it. So it's 0.8 from 0.941, our factor, plus 0.3 with 1 minus 0.941. Okay, so 94.1% of the emissive power is from 0 to 2 microns at 5,800 Kelvin, and about 5.9% is at 2 to infinity micron wavelengths at 5,800 Kelvin. So we do that, and we get 0.771. So that's our total absorptivity of the solar emissive power for our surface. Okay, so ours look like something like here that we ended up getting here. All right, so we go back up here, and we just did this, okay? So we need to either figure out the sky's absorptivity or the plate's emissivity, because it's diffuse gray. So that meant, I didn't actually specifically write that down, but that meant that is equal to that. Okay. All right, so let's say we do the sky's absorptivity. All right, so we had this. This is our absorptivity definition, okay? If we're just looking at over wavelengths because it's diffuse, so we don't have to worry about direction. So in our case now, it's the sky, so we need to change this. But what can we, this irradiation G, now what do we change that to? when we're dealing with the skies, absorptivity. Let's take a look at what we did above here, right? Any ideas?
You change it to a function of the temperature of the sky.
Yep. Okay. And it's the emissive power. So we're just saying E wavelength of the black body, since the sky is emitting as a black body. And we say wavelength, and then the temperature of the sky, I think it's 233 Kelvin, -40. Okay. So we're basically saying the irradiation that's hitting the surface from the sky is the same as what the black body is of the sky, since the sky is emitting as a black body, right? So what ends up hitting the surface is the same as what's leaving that sky as a black body. Okay. All right, so we can do then same thing we did in the last one. We have this ratio. Oh, so I should say this is for the sky. And break it up into two. All right, so we have these two ranges now. I'm gonna put 2. From 0 to 2 microns, 2 to infinity, right? Same kind of thing we did above, right? So now, if we need to get this F factor again, we said we get that from table 12.2, right? And we need wavelength times temperature, right? So what wavelength do I use?
2 again?
2. What temperature do I use?
233.
Yeah, so now we use 233, right? So even though it's this F factor here looks like the same above, this is a fraction of the emissive power from the sky. So don't reuse that F factor above. We got to calculate a new one. We get 466 micron Kelvin, right? So now when we go to our table, our factor is actually approximately 0. Okay, so it's going to look like, if we again plotted that thing we had above, that curve of what those two columns look like, we're down here somewhere for that factor. We're above, we were, way far in. We were way more to the right because we had ended up with 0.941 of the emissive power over that range. Here at 233 Kelvin and 2 microns, we're barely anything's been emitted of emissive power. Okay, so basically zero. So if we put this together, then we have 0.8 and 0.3. Okay, and we see then that the sky's absorptivity is just 0.3. Okay. All right, so what does that tell us then? What's our emissivity of the plate?
Point 0.3.
Yeah, 0.3, since we had the gray diffuse. We have 0.3, right? All right, so that gives us that. We could have also went and got the emissivity from the table by using, instead of, so this is the assumption of gray, or sorry, diffuse and gray. I should say diffuse first. Diffuse and gray. Well, that gives us that it's equal, but we could have also just used the assumption of diffuse, which tells us that the absorptivity at a given wavelength, let's draw that a little better, is equal to the emissivity at a given wavelength, and just changed our figure here of wavelength versus absorptivity to emissivity, and went through the same step. So we could have went and just drew our plot doing that. Okay, and here we have 0.8 and 0.3. Since they're the same at any given wavelength, it's the same as the figure above. And we could have went through and did our emissivity. Okay, and we went through and again got our wavelength times temperature. In this case, it's going to end up being, we have what, 60? So 333 Kelvin. So we would have got 666. And then from our table, our factor would have been still about 0, okay? Because we're at 666 before we were at 466. So we're still going to be somewhere down here, okay? Where solar, we were up at 11,600, right? So 2 orders of magnitude higher, which is where we got to our point where we were way over here, okay? All right, so anyways, we have our absorptivities and emissivities, right? So if you go back way back up here, we had one, so we had the other, right? We could have solved for emissivity and said it was equal to the sky. We did the sky and said it was equal to the emissivity, the sky's absorptivity instead of, but either way, all right? And we also did it separately if we wanted to, okay? So we didn't have to make the gray assumption, even though it's valid in this case. So then the last unknown is our heat flux of our electric heater, right? So we just solve our COE now that we have all our parameters. If I can scroll all the way down to where we ended up. So we get 342 watts per meter squared. Okay. Any questions? Okay. Let me off easy here.